Thermochemical Processes An Overview Part 4 Lecture by Dr.G.Subramanian, Chief Scientist Retired, CSIR, Central Electrochemical Research Institute. In my previous lectures about thermochemical processes and overview part 1, we highlighted about thermochemical processes such as sludge thermochemical treatment, which includes oxidative and non-oxidative processes. Under oxidative process, we have incineration, wet air oxidation, and supercritical water oxidation. Under non-oxidative process, we have gasification, that is partial oxidation, hydrothermal processes, which can be classified as hydrothermal carbonization, hydrothermal liquefaction, and hydrothermal gasification. Finally, pyrolysis. And oxidative thermochemical treatment of sludge, we have incineration of sludge. In that, we have seen a video about Autotech Sustainable Sewage Sludge Incineration Plant for the Canton of Zurich, the largest and most advanced incineration plant in Switzerland. Completed in 2015 with an annual capacity of 1,100 tons. Complies strictest environmental standards set by the European Union compliances. Then, wet air oxidation of sludge. This process does not generate secondary pollutants. Example, Zimpro process from Siemens and TOP process technology from company 3V Green Eagle. Further, we have supercritical water oxidation of sludge. Supercritical refers to the state of water within a specific region of pressure greater than 218 bar and temperature greater than 374 degrees centigrade. States of water as a function of temperature and pressure. Triple point, critical point, and supercritical fluid. Examples: supercritical water oxidation process for sewage sludge treatment using aqua-Critox technology. Then another lecture in continuation of the previous one, that is thermochemical processes and overview part 2. In that, we have dealt with pyrolysis, an example of non-oxidative thermochemical treatment. An example of the pyrolysis process for sewage sludge is Eisenman pyrobuster, demonstrating thermal treatment of sewage sludge. Then how pyrolysis works. It has different types: slow pyrolysis, intermediate pyrolysis, fast pyrolysis, and hydropyrolysis. A standard design for a pyrolysis process comprises a reactor, a cyclone for separation of the particulate solids from the flue gas stream, and a condenser to retain the liquid bio-oil fraction. The gases generated by the pyrolysis reaction are either condensed to form the bio-oil fraction, or if non-condensable, either collected for export or used to heat the reactor. There is increasing interest in the use of microwave heating as an alternative to conventional heating methods. Further, my next lecture on thermochemical processes and overview part 3, that we have dealt with sludge treatment through gasification and how gasification works. Gasification aims to completely convert the carbonaceous content to a solid ash and a clean combustible gas product for use locally. Countercurrent gasifier reactor showing 4 steps of organics conversion. And further, gasification produces a single clean product, can make it more attractive than pyrolysis for installation in a wastewater treatment works, since the gas is easier to reuse directly than is a combination of oil and gas. Hydrothermal processes. Hydrothermal processes, shortly called HTPs, for treating sludge employ elevated temperatures and pressures in wet conditions and in the absence of oxygen. They can be employed for two different applications. One is pre-treatment of sludge prior to anaerobic digestion and substantial conversion of organic carbon to useful combustible products. Hydrothermal pretreatment for anaerobic digestion employs lower operating temperatures and pressures than the conversion processes. Unlike hydrothermal processes for carbon conversion, they are not designed to substantially reduce the organic carbon content. Hydrothermal processes for organic carbon conversion can be classified into three main regions of the water pressure temperature phase diagram, according to the main product being targeted. They are hydrothermal carbonization, shortly called HTZ, which favors the solid phase as the main product. Then hydrothermal liquefaction, shortly called HTL, which favors the liquid phase, and further hydrothermal gasification, shortly called HTG, which promotes a gas phase product. So this picture clearly illustrates the regions of hydrothermal carbonization, hydrothermal liquefaction, and hydrothermal gasification. It is a pressure temperature curve. Hydrothermal processes and approximate regions of operation with reference to the pressure, temperature, water phase diagram. There you can clearly see HTZ and HTL and HTG and supercritical water gasification. So at this point you can see critical point, that is which is 374 degrees centigrade and 221 bar pressure. In common with pyrolysis, the different product phases, that is solid, liquid and gas, from hydrothermal processes are favored by different conditions of temperature and pressure. Unlike pyrolysis, however, hydrothermal processes can operate with a feed sludge of high moisture content, the water being kept in the liquid state during hydrothermal processing through the application of high pressures. Hydrothermal carbonization and hydrothermal gasification are sometimes respectively referred to as wet torrefaction and supercritical water gasification. By definition, torrefaction is a dry process, whereas hydrothermal processes necessarily take place in hot, pressurized water and involve a complex mixture of chemical reactions which include hydrolysis. The nature of the solid char end product therefore differs substantially between hydrothermal carbonization and torrefaction. The end hydrothermal carbonization product is called hydrochar to distinguish it from biochar generated by torrefaction. The use of hydrothermal processes as a means of converting the sludge organic carbon into useful combustible products directly represents a relatively new approach to resource recovery. There are few full-scale operating hydrothermal processes plants for full sewage sludge conversion to useful end products, though demonstration, otherwise full-scale hydrothermal carbonization plants exist based on hydrothermal cycle and terra nova technologies. This contrasts with substantial number of hydrothermal process installations for anaerobic digestion pretreatment first observed in the mid 1990s and the large number of incineration plants. While there are a limited number of full-scale examples of hydrothermal process sludge processing plants installed globally, The process has been extensively investigated. Reported studies of the various hydrothermal process types at laboratory and pilot scale indicate a very wide range of operational parameter values employed for sewage sludge hydrothermal conversion. This table describes hydrothermal process operating parameter values from left to right. Process, abbreviation, temperature in degree centigrade, pressure minimum in terms of bar, residual time, product yield. So under this process we have hydrothermal carbonization, shortly called HTC, temperature range 200 to 300 degrees centigrade, pressure minimum in terms of bar. It means minimum pressure determined by the pressure temperature relationship for maintaining water in liquid state, about 16 to 88 bars, and residual time is 0.5 to 8 hours. Product yield 45 to 98% yield hydrochar. Next one is hydrothermal liquefaction, shortly called HTL. Temperature range 250 to 400 degrees centigrade. Pressure minimum 41 to critical pressure. That is, critical indicates the maximum temperature exceeds the critical temperature such that the water exists in the supercritical state. And residual time 5 to 30 minutes. Product yield 35 to 55% yield bio oil. The next process is hydrothermal gasification, shortly called HTG. Temperature range 380 to 550 degrees centigrade, and pressure minimum pressure in terms of bar, that is critical 2. That is, critical indicates the maximum temperature exceeds the critical temperature such that the water exists in the supercritical state, and residual time is 0.25 to 2 hours. Product yield is 16 to 50% of hydrogen. And finally we have catalytic hydrothermal gasification, shortly called CHTG. Temperature range 380 to 550 degrees centigrade. Again, pressure minimum critical. That is, critical indicates the maximum temperature exceeds the critical temperature such that water exists in the supercritical state. And residual time is 0.25 to 2 hours. Product yield is 30 to 75% of hydrogen. Under this catalytic hydrothermal gasification, it employs a catalyst to promote production of the desired hydrogen product. Hydrothermal carbonization, shortly called HTZ. It converts sludge predominantly into a carbon-rich hydrochar solid product. The process is conducted at temperatures generally between 180 and 300 degrees centigrade. Over this temperature range, corresponding pressures of 10 to 88 bar must be exceeded to ensure that the water is maintained in the liquid state in accordance with the pressure temperature water phase diagram. Reaction times ranging between 0.1 and 4 hours have been employed. The precise conditions of temperature, pressure and time selected depend both on the feed sludge quality, the target yield and characteristics of hydrochar product. The treatment temperature T in degree Kelvin and time T in seconds are sometimes combined and expressed as the severity factor, that is F is equal to 50 T power 0.2 and E power 3500 by T. Higher severity factors favor a higher hydrochar carbon content, thereby providing greater latent energy in this phase. The structure of the hydrochar also changes with the temperature. There are a few small full-scale hydrothermal carbonization facilities in operation. The process has been implemented for the conversion of municipal solid waste MSW into a useful hydrochar product. More recently, hydrothermal carbonization studies have been focused on phosphorus recovery from the hydrochar. Phosphorus can be recovered from the process by acid addition, encouraging the phosphor to transfer to the aqueous phase from which it can then be recovered by precipitation. An example is PHOS4 green process from German company GLAD, which generates a usable granular phosphate-based fertilizer from hydrochar. Terra Nova, first commercial large-scale hydrothermal carbonization plant for sewage treatment in Jining, China. So the below given YouTube video link provides you more information about the video. Hydrothermal liquefaction, shortly called HTL. Hydrothermal conversion via liquefaction takes place generally at temperatures of 250 to 400 degrees centigrade and pressures above 40 bar. The product is a highly viscous liquid, that is a bio-oil, used as either a pure chemical or an additive in diesel fuels. Hydrothermal liquefaction has been extensively investigated for cleaner biomass feeds and specifically for microalgae. Microalgal technology for renewable energy and resources represents an extremely significant area of academic study. Hydrothermal liquefaction for sewage sludge treatment is still largely under development. However, a $12 million Australian dollar sewage sludge fed hydrothermal liquefaction plant is under construction at Yarn in Australia. This is the time of writing this article. So this video explains how turning goo to fuel using hydrothermal liquefaction process at Pacific Northwest National Laboratory. The Earth takes millions of years to turn biomass into oil, whereas researchers at Pacific Northwest National Laboratory can do it in minutes. The below given YouTube video link provides you more information about the process in which it has been done in this laboratory, Pacific Northwest National Laboratory. Another video explains how waste biomass has been converted into useful biofuels. The video link has been given at the bottom. High flex fuel. Here, advanced biofuel production via hydrothermal liquefaction of various organic feedstocks. From waste biomass, it is converted into biocrude, then it is further converted into useful biofuels. Hydrothermal gasification, shortly called HTG. Hydrothermal gasification represents the highest temperature hydrothermal processes, operating at temperatures up to around 550 degrees centigrade. Since temperatures exceed the critical point for water, the process is sometimes referred to as supercritical water gasification, shortly called SCWG. Analogous to supercritical water oxidation, which operates in the same supercritical region as hydrothermal gasification but employs somewhat higher temperatures due to the exothermic nature of the oxidation reactions. The primary product of hydrothermal gasification is a syngas containing hydrogen and carbon monoxide as the primary constituents. At near critical temperatures, that is up to 500 degrees centigrade, formation of the syngas is substantially increased by addition of catalysts such as metals, hydroxide, or activated carbon. Although effective, these catalysts, that is in particular alkaline metal salts, can cause scaling and corrosion problems. The generation of products is otherwise affected by the temperature and residence time. In France, nearly about 100 million tons per year of liquid biomass waste has been converted into useful gases using hydrothermal gasification processes. So this video, the below given video link details briefs about the process. It has been successfully implemented in France. Thank you very much for watching this video, and thanks for your patience.